All right, let's get started. Welcome back. Hope you all had a good break. So our next session is protocols. We have two papers in this session, and each talk will have 20 minutes, including Q&A. So please post your question in the Q&A tab. If you have any questions. Um, so the first talk is bad USB-C, revisiting bad USB with Type-C. Uh, the speaker is Hongyi Lu from Southern University of Science and Technology, China. So Hongyi, the stage is yours.
Okay. Hello everyone, I'm Hongyi Lu and I'm here today to present our work, BadUSB-C, Revisiting BadUSB with Type-C. This is actually a course project of computer security instructed by Professor Zhang in Southern University of Science and Technology. Here is the outline of my today's presentation. First, we will go through some background about USB protocols. Then I will introduce the design of our BadUSB-C and the prototype we implemented to test its efficiency. After that, I will talk about a case study of a real-life scenario of sharing power bank, where we simulated stealing private data using BadUSB-C. After the case study, I will also discuss the limitations, mitigations, and the responsible disclosure we make to Huawei. Lastly, I will summarize and conclude this presentation. USB, short for Universal Serial Bus, it is kind of a ubiquitous protocol nowadays. You can use it to connect to HIDs like keyboard or mouse. You can use it to connect a power bank and charge your phone when going outside. And you can also use it to carry data around with a flash drive. What's more, with Type-C connector introduced with USB 3.1, you no longer need to face a massive ball of cables. All you need is just a single USB Type-C cable. But just as the saying goes, with great power comes great responsibility. There are all kinds of vulnerabilities were discovered during the development of USB protocol. In 1996, USB 1.0 was announced with the support for basic HIDs like keyboards and mice. At that time, the BadUSB attack is already possible as there are few authentication mechanisms in USB protocol. In 2013, USB 3.1 was released with a major change in the connector standard. In USB 3.1, a new connector standard called USB Type-C was introduced, which allows transmission of video data like DisplayPort over a USB cable. This also paved the path for our today's work, USB-C, or BadUSB-C. As our work is an extension to the original BadUSB attack, now I will introduce the traditional BadUSB attack and its limitations. BadUSB attack is an attack presented on Black Hat 2014. It abuses the lack of. So it's lost at here, right?
Yes.
Okay.
I think you just started the introduction of bad USB.
Okay. Okay. So as our work is actually, okay, let me go back. Okay. So as our work is an extension to the original BadUSB attack, now I will introduce the traditional BadUSB attack and its limitations. BadUSB attack is an attack presented on Black Hat 2014. It abuses the lack of authentication of USB protocol to trick the victim's device into believing a flash drive is actually a keyboard, thus executing malicious commands such as reversal shell. But it has a major drawback. As we can see here, after it executed a malicious command such as a reversal shell, the attacker cannot actually obtain any feedback until the shell is established, which largely limited this attack. And we summarize the drawbacks of traditional BadUSB attacks as follows. First, due to the lack of a stable feedback channel during the attack process, the attacker cannot view the attack progress, thus cannot carry out process attacks. Secondly, as the BadUSB only provides HID emulations, it is almost impossible for BadUSB to interact with GUI components such as the button. This severely limited the potential of BadUSB on mobile devices, which usually does not equip with a powerful command line interface. Apart from that, to establish a connection between the attacker and the victim's device, such as a reversal shell, BadUSB typically requires the host network usage, which may be detectable to IDS intrusion detection system or stopped by firewalls. Here, we introduce the design of our BadUSB-C and how we solve the three limitations of BadUSB. As we can see here, the BadUSB-C is connected to the victim's device using a USB Type-C cable, which can transmit both video signal and HID signals. In this way, our BadUSB-C can collect the video stream. Okay. In this way, our BadUSB-C can collect the video stream of victim's device and build a stable feedback channel using the video capture card listed here. This forms a video stream path of our BadUSB-C and solves the first limitation of the original BadUSB attack. What's more, with this video feedback channel, the HID emulator here now can emulate not only keyboard but also mouse to perform GUI interaction on the victim's device. This solves the second limitation of the original BadUSB attack. Lastly, as we can see in this figure, our BadUSB-C also uses an individual Wi-Fi/GSM module to transmitting data between the attacker and the victim's device. This avoids being detected by the firewall or IDS on the victim's devices. Here is a prototype we built to test the efficiency of our BadUSB-C. Here, A stands for the victim's device, which is a Huawei smartphone. B is a compact version of our BadUSB-C after it is assembled. And on the right is the components of our BadUSB-C. One is the USB-C hub we use to connect all the other components. Two is a Raspberry Pi as the onboard computer to pre-process the video data to avoid transmitting too much data to the attacker to save network bandwidth. Three is the auxiliary power bank, which provides power for both BadUSB-C itself and the victim's device. Four is the video capture card that captures all video streams transmitted by the victim's devices. Five is a chip from ATMAG and as the HID emulator and the Wi-Fi chip. We also conduct a case study of sharing power bank, which is a popular service in China. When you are outside and your phone's power is nearly depleted, you can rent a temporary power bank to charge your phone and return it later. Here is a typical attack procedure of BadUSB-C on sharing power bank. First, the attacker can rent a power bank and replace its internal with BadUSB-C. Then the attacker returns the tempered power bank to the rental station. After another naive user borrows the modified power bank and connect it to his or her own devices, the attacker can have complete control over the victim's device. We also performed an experiment on a Huawei P30 Android smartphone, and 11 applications were selected and tested in the following steps. First, we log in a test account and keeps all the default settings. And then we attach BadUSB-C to the test device. And we simulate victim's daily usage of the application and see what we got. Here is some screenshots of the leaked informations. On the left is a screenshot we obtained from the status page of PayPal application, which leaked the financial status of the victim. On the middle is a screenshot of WeChat payment QR codes, which can be used by the attacker to perform transactions without victim's permission. On the right is a screenshot of Telegram, which leaks the victim's chat history. And here is also a table summarizing the leaked information during our experiment. In social network applications such as WeChat and WhatsApp, the attacker can obtain the context and chat history of the victims. In financial applications like Alipay and PayPal, the financial status of the victims is leaked. During our experiments, we also find that our BadUSB-C has the following limitations. First, BadUSB-C cannot actually bypass biometric authentications like fingerprints. And second, BadUSB-C requires DisplayPort over USB-C feature to work, which is a rather new feature and currently only well supported on flagship phones. Lastly, BadUSB-C may incur notifications on victims' devices and be discovered. To mitigate this vulnerability, we also proposed a novel mitigation for this kind of problem. This is to divide UI rendering into two layers. One is the sensitive layer and the other is insensitive layer. As this figure suggests, sensitive contents such like password and the keyboard used to input it are only rendered on sensitive layer and will not be transmitted to any external monitors. Thus, this mechanism can effectively mitigate this issue. After this vulnerability was discovered, we immediately contacted Huawei, who later assigned a CVE entry for this vulnerability. And this is an email of Huawei's response. And we also applied for the bug bounty program of Huawei, and who gave us a generous reward of over $4,500. Now, mitigations for this vulnerability has already been deployed, which requires users' authentication before allowing any external USB devices to get the video stream. And we summarize our work as follows. Firstly, we explore a new attack scheme leveraging the latest feature of USB protocol. Secondly, we conduct a real-life scenario study of sharing power bank to test BadUSB-C's efficiency. Lastly, we propose a novel mitigation named isolated UI rendering for our BadUSB attack. Okay, thank you for your attention. Do you have any questions?
Thank you so much, Hongyi. I guess it finally works. We have one question in the chat. Jose has a question. What are the reasons of the DisplayPort over Type-C requirements? Does Type-C not support transporting HDMI?
Okay, so you want to ask the latency of the USB-C transmission, like its bandwidth and the latency? Okay, so during our experiment, we find that the latency of USB-C is fine. It can transmit DisplayPort and HDMI okay, and almost have no latency. Our main one of the limitations of our BadUSB-C attack is that the network, okay? So we add a Raspberry Pi to solve the network latency problem, which is to pre-process the video stream before we transmit it, like extract the useful frames and do not transmit the whole video stream, okay? So I'm not sure if that answers the question.
I think I'm not sure it fully answers. Maybe Jose, you can type whether he answers your questions or not. And there is another question from Virgil. Can you also emulate a mouse plus cable plus USB-C stick to copy and run a malicious APK, for instance, and bypass the confirmation UI by emulating a USB-C mouse?
Okay. Yes, we tested it. It can actually bypass most of the authentications, but as I mentioned, it cannot actually bypass biometric authentications. So for mobile phones equipped with like fingerprints, it's hard to actually bypass such authentications. And but if it's already in like is not in the lock screen. So you can actually plug in the all the emulated devices such as mouse, keyboards, as long as they are connected to the USB-C hub, which will in charge of the whole communication process. Yes.
Okay, we have two more questions. Is this really a failure or vulnerability on the side of USB? This seems more like a vulnerability in plugging unload device. Is it even possible to separate valid or invalid USB devices? What are your thoughts on that?
Okay, so I believe that this is okay. During our experiment, we actually find that USB OTG, which is use the smartphone as actually as a host of the USB protocol, can actually differentiate uh, different functionalities. For example, when you connect your phone to a computer, it will ask you to transmit files or to use it only in charge. Okay, it can separate these. I believe is actually overlook in USB protocol designs. I believe the authentication should be added to USB protocol designs. For example, when you plug in unknown devices, it can promote the users to input its functionalities, such as I believe there is a work called Good USB who is doing who is actually done that. Okay, and I personally I think this vulnerability is rather obvious, but I also believe that USB protocol can be refined to avoid such problems. Yeah.
Okay,
Oh,
makes sense. So one last question: how can trusted or untrusted screens be differentiated?
yeah. So I believe he's asking about the isolated UI rendering. Yeah. Uh, in in our paper, we actually mentioned that it should be the developer who is deciding which should be rendered in. Oh, okay. You mean trusted? Oh, okay. Sorry. So, in mobile phones, we believe that the internal screen of the mobile phones are the only trusted screen. I mean, in mobile phones, people does not usually input their phones in an external screens. It's real happens. So we believe in our proposal we only plan to use the inner equipped screen of the smartphone as the trusted screen. Yeah, but you can also design a mechanism to, for example, trust the other external screens, but it requires the user interactions. Yeah.
Okay, so we are already 4 minutes past, so I guess we still have several more questions in the chat. So maybe Hongyi, you can type your answer in the chat. So thank you again for the talk. Very nice work.